All right, what is up, guys? Welcome back to my YouTube channel. This is Lab 2 for Physics 2. My name is Matthew Mazzucano. Let's get into it. All right, so an introduction to this lab. It's the same exact thing that we did for Lab 1, except we're taking a deeper look into interactions between the two charge tapes. Instead of treating the electric force generated by the bottom tape as a point charge, we're treating it as a distribution of charge along the entire length of that bottom tape. Going more into it, so the physics principles I used was Newton's second law, Newton's third law, and Coulomb's law. Newton's second law comes into place when the top tape is not moving, net force is zero. So we know we can use Newton's third law that every force is equal and opposite. So since it's not moving, we know that the electric force we found in Coulomb's law is equal to the gravitational force because they're equal and opposite. Assumptions we made: each of the U tape has the same charge, the charge is uniformly distributed, and air resistance is negligible. Procedure: created multiple charge tapes of equal length by ripping off electrons from the tapes. Position the top tape so that it hung slack from two boxes to raised points. Held the bottom tape underneath the top tape, brought it close until the top tape was suspended in equilibrium, and then we measure the distance between the tapes to find our R value that we use in our equations. Alright, so I made sure all the tapes are the same length so that we had the same mass. The distance from the bottom tape and the top tape when the top tape was floating and in equilibrium was 0.02 meters, aka 2 centimeters. And by using the mass of the tape, I'm able to find the gravitational force, negative 0.002116 newtons. And since at the equilibrium position, the gravitational force is equal and opposite to the electric force, we know that the electric force is going to be equal to 0.00216 newtons. These are negative and positive, as if the y direction is upwards. So negative 0.00216 newtons is pointing downwards towards the ground. That's why it's negative. Positive is pointing up towards the sky. All right, more into it. Coulomb's law, we already know that. Rearrange it to find the charge of the bottom tape, plug in our values. So the initial thing we find when we're just treating it as a point charge is 9.6977 times 10 to the negative 9 coulombs. However, this is not enough to actually balance it out, so I need to increase the charge to losing track. Okay, we need to increase the charge so that actually balances out the force, the gravitational force. I kept increasing it until we got to 2.419 times 10 to the negative 8th coulombs, so a good amount bigger. Here's the output for lab 2. Here we see that now the electric force is balancing. The electric force represented by this white arrow is balancing the gravitational force represented by this yellow arrow. Here we have the top tape and the bottom tape. They're represented as like multiple point charges to make up a line charge. All right, conclusion. What if in the previous lab you modeled it as just single point charges, compare the estimated value. So the charge of the tapes is around 2.5 times less when modeled as point charges instead of a line charge. Why? The two computational models for Q will be different. Why are they different? Which value is more real? The model of tapes using line charges is, instead of a point charge, more accurately represents the electrical force that we would see in real life. So the line charges model's value is much more likely to be closer to the real value than just using a point charge, which is not a little bit lazier. All right, that's all. Thank you for coming to my YouTube channel and watching my lab presentation. Have a great day.